the title of this talk of this seminar is exploring the fastest chemical reactions using ultra-short laser pulses, an outlook for quantum computers based on chemistry. So it really sounds very interesting. And maybe before the speaker, Michal Belina, will start, I will say a few words about him. So Michal Belina, he is a research assistant at the Quantum Computing Laboratory at the IT for Innovations National Supercomputer Center. So he's currently moving to the field of quantum computing from computational chemistry, and his alma mater was University of Chemistry and Technology in Prague, from which he graduated in 2020. He's currently finishing his PhD in computational chemistry at the same institution. So his thesis focuses on describing relaxation processes following substantial electron excitation and or ionization, including the ionization of core electrons with a particular emphasis on systems with hydrogen bonds. So maybe it's enough as an introduction of the tutor or of the speaker. And now I want to give the floor to the Michal Belina to start the talk. Okay, it's yours, Michal. Good luck.
Good afternoon, everybody. Thank you for introduction. And yeah, I would like to start this seminar, which Jirka already somehow described. And I've prepared a slide about me, but almost everything was already said. So I would like to show you some content of my talk. It consists of two a little bit separate parts. In the first, I will describe some what I did on my PhD, and it will be focusing on how are the fastest chemical reaction tracked, or how can be tracked, and some other things. And it will be I will show some three case studies or three different things. And then in the second part, I will briefly speak about quantum computer architectures based on molecular spin, or basically the single ion magnets, and a second quantum computer based on nuclear magnetic resonance. So to start with, I would like to say a really basic question. How do you define a fast process? Generally, it's something that's happening too quickly to watch, or at the same time scale. And this ability to watch, or the time resolution of which humankind were able to observe processes around, of course, change during the time, right? During the evolution of science and so on. And the first device that was able to beat naked human eye in this time resolution was this phosphoroscope, invented 200 years ago, and it was just by rotating this clutch. You can rotate some splits here in this chamber, and you can reveal whenever some solids show phosphorescence or not. But later, still some reactions or some chemical processes were considered to be immeasurably fast, and it's for example, in 1930s, it was this very famous, well-known chemical reaction, neutralization, in which some acid and bases reacts to create water and some salt. Yeah, this is one of the simplest reactions in which the proton or this H is moving from something else to OH to create water. So this is some prototypical reaction, but in 1930s it was considered to be immeasurably fast, and this was written in some textbook, and it encourages Manfred Eigen to dig into this field of chemical reactions, measuring chemical rates, and he find way how to do another step in increasing the time resolution, and he did it through some periodical disturbing chemical equilibria, either with some electric pulses, repeated electric pulses, or with pressure pulses and so on. So generally, he said that this reaction is driven by um, only by the movement of these ions in water, um, but um, how fast exactly is transfer of just one atom was still hidden. And of course, the another large step forward was by inventing lasers and pulse techniques, which allowed us to create light pulses with width of 43 attoseconds, which is 10 to the minus 18 seconds. And we can use these pulses to interact with matters, interact with molecules, with ions, and then observe something happening. I would like to apologize. I have cough, so for it, sorry for disturbing with me coughing a little bit or a lot of whatever. So I would like to continue with a brief description of some experimental setups or experimental devices that are used, and first of them is this free electron laser, which is somehow how to call it, a laser on steroids. I would like to call it like that, because it can create really short pulses as well as lasers, but it allows precise tuning of energy. Right? This is a wavelength of outgoing radiation, and this K parameter, oh sorry, can be easily tuned and therefore adjust this outgoing energy of radiation. And the whole thing works that beam of electrons accelerated to almost speed of light, velocity of light, is wiggled in periodical repeated boundary magnetic field, and this wiggling of charge creates electrons, creates photons, which are then collected. Just to show you this kind of device, that there are not there are not many of these devices in the world, because for example in Hamburg, DESY, one needs this device is almost 3 kilometers long, so one cannot fit it in every building, right? So with some knowledge how to create laser pulses, I would like to say something about bulk versus cluster experiment. You can this is the basic. You can divide these approaches whenever you address some small system like this water dimer about which I will talk later, or you have some just droplets of water, and the really huge advantage of this small system is that you know almost precisely what do you have, and you can measure the outcomes of any reactions. You can charge these molecules and measure the ions, measure kinetic energies, measure the yields. Uh, if something happens in the middle of this droplet, water, well, you can track it with some spectroscopic methods, but there are lots of other interactions that prevents you to observe things that directly. And why are all these things interesting, or why do we deal with water and interaction of water with radiation? So here is depicted the scheme of what's happening with water molecule after absorption of photon, which has enough energy to ionize it. So the thing is that this scheme was discovered from the bottom to the up, right? Because first, in almost 100 years ago, we had techniques how to observe some reactants, some products of reactions in this almost microsecond time scale, and one need to go step up and step up to go to the initial processes, and to just know what's happening immediately after the collision of water and photon. And this is very important, especially for precise modeling of some large chemical schemes, or if you want to know what is the lifetimes of some reactive species, like how long will OH radical will live and so on. But on this femtosecond time scale, we are more involved more interested in what's happening uh, on like the electronic structures. So with this, I would like to go to the first study. I will show you, and this is called direct tracking or ultra-fast proton transfer in water. And this is generally the reaction which are we interested in. The we chose this water dimer as a playground, and after removing one electron, we created the H2O plus, and we were interested in what's happening and how fast this proton from the previously ionized water transfer to another. So what was done in the past was that the time resolution of these experimental methods were too low. And for example, in 2005, there was still only upper boundary known for this chemical rate, that it was estimated that it's faster than 1 picosecond. A few years later, there was another experiment conducted together with some theoretical study. And again, the experiment just saw the outcomes. So they lowered the boundary once more. And in 2020, the first concrete value for this proton transfer rate was published in this study. And it was something about 46 femtoseconds. A year later, a different study, more looking more at these two species, not directly at the proton, was published with significantly larger time, and this one might see some kind of discrepancy. But as these both studies were done in bulk water, it wasn't sure what exactly is happening, right? They were able to use some spectroscopic methods to measure the evolution of the progress of this chemical reaction, but The thing is that we wanted to have a look at the smallest possible system, which can be precisely modeled, and the outcomes of the reaction can be really easily tracked. So this is the whole scheme of reaction that was considered. We prepared water. The experimental colleagues prepared the water dimer, like molecular beam of water dimers, collided with beam of photons. This causes to electron to be emitted, and subsequently the reaction was observed. I'm sorry. And we were interested not only at this first part, how fast the proton transfer, but also on what's the dynamic on this, what's the of these oxygen species, how they interact with each other, and so to continue, I need to describe you the electronic structure of water, as your listeners are from different fields. This is the molecular orbitals of water, and this energy is roughly the energy you need to add to the molecule in order to remove an electron. And this ionization cross-section says that with photon with enough energy, it means more than this 1846 eV. So, sorry. That the probabilities of ionizing from different molecular orbitals is the same. So the light pulse with 24 EVs was chosen in order to address all these valence molecular orbitals. In this slide, I will show you the experimental design. What was the initial thoughts? How can the reaction happen? What can be the outcomes, and so. And the main experimental colleague of ours was Kirsten Schnorr, who is now working in Bolshar Institute. The experiment was done in pump probe setup. So there were two laser pulses. One ionizes the molecule, and then other do some other ionization. And so here this 24 EV pump causes to ionization of one electron. And there are two basic scenarios that can happen. Let's say that this water molecule was ionized. The plus charge on the molecule causes proton to transfer to this H3O plus, and by this process the water dimer relaxes, right? And then another pulse comes and ionize and removes another electron from the system. And here is crucial, the energy, because it was selected such that it cannot ionize this species for the second time. It cannot create H3O plus plus, but the energy is enough to ionize this OH radical. So the outcome of this schematic depiction of the reaction is this H3O plus and OH plus couple. This, of course, is two singly charged small molecules and nothing else than just Coulomb explosion happens later. But another thing is that this second pulse were delayed from 0 to 300 femtoseconds. And the second scenario happens when the probe pulse comes in the middle or before the proton could transfer to another molecule, like for example, it comes in this arrangement, ionizes this previously unionized, sorry, I misclicked somehow. It's not good. So yeah, so let's assume that let's assume that the second pulse comes in this arrangement, ionizing this molecule and preventing the proton to transfer. And so this another reaction channel without proton transfer is H2O plus H2O plus. So we have two different reaction channels in here, one with proton transfer footprint in it, other without. And these outcomes of this experiment were observed with reaction microscope. It means that this coincidence reaction microscope, this is the experimental device that allows to track ions originated from the same water dimer. So you can by getting the energies, by measuring the energies of this fragment and this fragment, you can get the energy of this Coulombic explosion, and most importantly, you can get the ion yields. You can compare how many of the reactions went in this way and how many in this way. So this is just another slide of experimental setup. As the same energy was used to pump and probe, there was just two pulses scanned continuously from minus 300 to 300 femtoseconds, and one always counts as a pump and the second is a probe. And this is the experimental device. As we are dealing with UV photons, the diameters or length of the device can be much shorter than the other than the free electron lasers from for X-ray photons. So these are the final results, and this is here we can see the ion yield of this H3O plus OH plus channel, the channel which has footprint of proton transfer in it, as a time as a function of time delay. And the green curve shows the experimental fit to this function, and we find that the estimated proton transfer time or measured proton transfer time is within the error bars, within the error of the previous study from 2020, and to somehow to verify the experimental scheme, we conducted the theoretical simulation or theoretical experiment the same way, and we got the very same results. These are data averaged from for all states. I will show it later. So one more insight into water dimer structure. Here is just very schematic depiction of electronic structure. These balls represent electrons. One of these columns belong to one water molecule, another to another water molecule, and with this 24 EV pump, as was shown previously, you can remove electrons from these 6 molecular orbitals. 3 for one water, but we have 2 waters, and the energies are almost the same. And so the hole can be at every level here. And this thing is or the experiment was was unable to distinguish which is the states are were populated, and so to have a look at it, we did simulations of the same event, and we copied the experiment in every step. So first we prepared some initial nuclear density of this water dimer, and to represent the initial molecular beam of experiment. Then we did non-adiabatic molecular dynamics, considering 6 different initial states, and each of these states represent a different molecular orbital ionized. And these dynamics in this singly ionized state represent what's happening after the first ionization. Then, as you already know that there were 2 ionization, we simulate what's happening after the collision with another photon, or absorption of another photon, and second ionization with this another molecular dynamic in doubly ionized state in this case. So with this we got our theoretical results. In here you can see the again a channel ratio as a function of time, and this channel ratio means so as we run so-called trajectory-based simulation. So it means what's the percentage or ratio of the reactions of the water dimer in different following different reaction path. So the most important here is the black curve, which represent the molecules which went towards the proton transfer. And you can see that when starting from the electronic ground state, the simply ionized electronic ground state, we got proton transfer time 40 femtosecond, which is with a great agreement with experiment. But when we started from the D1 state, here we can see the same figure on the left side, but on the right side, I put the results from D1 state. You can see that the proton transfer time is more than double comparing to this D1 state. So although this final channel ratio yield is almost the same, like here it is 85, here it is 80%. The proton is happening much slower. So it's really important in which electronic state you start. And just for curious, here is how it looked like when we started from the 5th excited state. And again, the proton transfer time was almost the same as in the when started from the 0 state, but the final yield were much lower as other channels contributed much more, and these other channels means like loss of hydrogen or even 2 hydrogen and other fragmentation that again were not observed by the experiment as they observed only those two channels. So with this, I'd like to show you what the evolution of electronic populations look like, because when you started in the 0 state, it was the some part of the molecules transferred to this D1 state, and the reason is that these D1 and D1 and D0 are degenerate, so it is quite expectable that this is the results of the simulations. And whenever we started from the D1 state, there was first some drop of the populations, but then again some stable state was found. When we started from higher excited state, the fast depopulation was observed. Here it is. Something about like the decay times was something like 15 femtoseconds or something like that, and similar can be observed here. And another way how we is okay. Yeah, oh, no, I stopped the presentation. Sorry, I will just continue it and find any question. So question is, how many molecules were included into calculations, and how their number of molecules per volume unit was chosen? Yeah, so there were only two water molecules considered, as this was the experimental setup. As I said, we wanted to compare the results of experiments in bulk water, in some water droplets, with the smallest playground possible. So this was really just two water molecules. But that's the same what was done in an experiment, right? They just want to have a look what exactly is happening. And as the experiment was done uh, in molecular beam, means that the density of the particles and molecules is really low, so you can assume that it's as is happening as in vacuum in gas phase. Or there is a pretty high vacuum um, in the reaction chamber. So this was done in the same way. So the simulation was done in gas phase. Yeah. To continue, I would like to um, show you that we compared the theoretical and experimental results in another domain, not only the time domain, but in energy domain as well. And these are the distribution of kinetic energies. What's the energy of the two fragments combined together? Um, yeah, for different time delays, and you can see that the general yeah, general features are well covered. For the longer time delays, there is a shift towards lower kinetic energies. So with this, I would like to go back to the previous studies I showed, and we found out that this proton transfer is really happening at this time scale, comparable to this study from Love et al. And this this 140 femtosecond are more um, um, it's not directly comparable to this, because they studied the movement of oxygen atoms, which is slower, which was observed to be much slower than this, even in our simulations. So yeah, the final challenge was to publish the study correctly. I mean, not to publish it, but to publish it correctly, because this is the name of my current supervisor, and it's a Czech name with some of these special signs. And first attempt to publish it wasn't all right. The second, third as well, and the final fourth attempt to publish it was approved by my supervisor. So one take-home message from this seminar is to you should pick your colleagues carefully if you don't want to have your publications delayed. So with this, I would like to move towards the other study, which is again studying proton transfer, but this time in cluster of one water and one pyro molecule, and this might be motivated a little bit more on the side what's happening if you replace one of the water with something much larger, and this pyro is like part of the can be found in some biomolecules. So it has some a little motivation in what's happening with within the bodies, but or living tissues, and so. But to trigger the proton transfer here, one need to not only singly ionize the cluster again, but to doubly ionize it, and just to state that it's not like real artificial ionizing the cluster to really high or imaginable degree. This doubly ionized state can be created after interaction of the uh, molecules with X-ray beams. So whenever you go to a doctor to have X-rays, so you can something like a double ionization of something similar to water pyro cluster can be happening in your bodies. So this system is quite interesting from the point of electronic structure, as the pyro is large enough to contain this double charge on itself in electronic ground state, right? This is if you have if you prepare the system in most relaxed electronic structure, the both electrons are removed from pyro unit, and one need to look at some higher excited states in order to find the localized state. I think, yeah. So yeah, I was looking at the time. With this, in this study, we used two different methods to ionize this water cluster, and first of them is electron impact ionization, where you create beam of electron collided with a beam of some molecule, and by the collision you remove electron or more electrons, and then you can cause some and then you can observe something happening, or you can cause ionization via strong field tunneling ionization, and this is as depicted here. This is just a very schematic depiction of potential around some atom, and when you put this atom in electric field strong enough, then you can like change this plane to some slope, or you could create something like this, and then electron as it behaves as it has a quantum nature. It can tunnel through this barrier, and then you create your ionized molecule. So here we combined two experiments. Again, we were looking at the dynamics of proton transfer, and after the collision of electron beam with this water pyro cluster, two channels were observed, one without the proton transfer and another with the proton transfer. And also there were some other fragmentation, but I won't discuss that. And as you can see here again is some kinetic energies of these fragments, distribution of these kinetic energies, and you can see some shift in this kinetic energy. So this has some information about what's happening within or before the Coulomb explosion. So another experiment was conducted in time domain when they use this strong field ionization and pump probe pulse. The advantage of strong field ionization is that you can ionize the molecule using like the really let's say casual lasers. You only need you need only very strong electric field induced by the photons. And what they measured is this 48 femtoseconds as a proton transfer rate. So this is within the again in the error bar or error boundaries, the very same proton transfer rate as was observed for water dimer, or what was observed in water bulk. And we simulated this in a similar way. And what you can see here, this is the channel in which the proton, the charge was initially localized here on the pyro, and you can see that the proton transfer is happening really fast. Again, most of the molecules undergo the transition within or the proton transfer within a few tens of femtoseconds, and on the other hand, when the charge is delocalized, nothing else than the Coulomb explosion is happening. So we we got from the simulations, we got roughly the same results as were from the experiments. So this will validate their approach. I might skip these things. And so what you saw in those previous two studies was that I was looking at the proton transfer, really the fastest chemical reactions, and it was happening in the same time scale, roughly 40 femtoseconds. And now only briefly, I will go through what I call the mass after absorption of multiple X-ray photons. And I'll be looking at the water dimer again. And now the thing is that we are not interested in these valence electrons, but we are interested more in these core electrons. Especially, or I mean, we are interested in ionizing these electrons, and to get energy of photon enough, one needs something like X-ray ionization or X-ray photons, and for this you need the 3 kilometer long X-free electron laser. So what's happening after the ionization of this core electron is so-called Auger decay. And when you remove photoelectron from molecule from the core electron levels, then within the a lifetime of 4 femtoseconds for oxygen, some electron from valence bands jumps in, and the excess energy is used to release another electron. Therefore, you can create with absorption of one photon, you can almost instantaneously, almost at the same time, create a doubly ionized system. So, and the guys, sorry, mean that Tiljanke and Ole Bjørnholm went even further, and they decided to look at this water dimer after consecutive absorption of two or even three X-ray photons. And the aim of this study was to again observe some structure-related properties of this dimer within ionization-related processes. So here are the four steps. What can happen when X-ray photons collide with are absorbed with water dimer? So first, there is core ionization. So one need to simulate this. One need to simulate the system in this core ionized state. Then within the 4 femtoseconds, Auger decay happens, and as the another water is really close, it can the second hole can be either on one molecule or second molecule. So then you need to simulate the evolution of this water dimer in doubly ionized state. Another X-ray photon comes, ionize again some core electrons, and causes the quadruply charged water dimer with these holes on, like, the electrons can be missing from different molecular orbitals, and it creates real mass in what's happening. And these are some predicted outcomes of what can happen after absorption of 1, 2, or 3 photons. So from the theoretic point of view, it's almost impossible to really precisely describe all of these channels or find the pathway, what exactly is happening in order to create this channel. So far we looked at the creation of this hydrogen plus, and OH plus channel. So sorry, this here it is, and here is like the cooking book, how what are the processes that leads toward this channel. One interesting thing that can be measured from this type of experiment are these momentum maps, and here you can see the relative momentum of this D plus. Here is the variant with heavy water. So this is deuterium. So you can see the momentum map of this D plus relative to the other fragments. And from this, one can again reconstruct the original geometry of the water dimer or the studied molecule generally. So to conclude this first part, I would like to state that I think the most important thing we found is that the proton transfer is happening at this 50 femtosecond time scale, almost independently on what's almost independently on the studied system, right? Because two studies of in cluster experiments and combined with previous studies in bulk water agrees on the same thing. And there are several other studies which were done by other groups. So with this, I think, or if you, if
question maybe?
because the other part will be a little bit separated. So if there are any other questions, so aiming at the first part, we are very encouraged to ask because there was only one so far. So
Yeah, we have a question.
yeah. That's exactly the thing. But yeah. And to the question or comment is, I'm thinking what you call mass can be related to impact ionization or cascade ionization. Yeah, that's exactly it. And but to identify processes which leads to different outcomes, that's that's I would call messy, or generally the plethora of final states or final products that are created um, uh, is uh, is what's messy. Introduces high entropy in occupations. Uh, yeah, yeah. Definitely. And as the energy, as the system has lots of energy, that there are the the Auger process I described is only one of some uh, other different processes that can happen. So I think that I will continue. Um, in this second part, I as I moved quite recently from this computational chemistry towards the more quantum computing things, uh, I was curious about what are the quantum computer architectures based on chemistry, or how can, let's say, even organic chemistry, how can contribute towards this really hyped area. And I will be discussing this molecular spin based architectures and nuclear magnetic resonant architectures. This part will be shorter than the first one, so uh, don't worry. So um, yeah, I would like to start with this so-called DiVincenzo's criteria, which states some properties which quantum computer generally should have, and I will somehow confront these criterias with what the different quantum computer architectures um, are good or bad. So, but for those who never saw this, the first thing states that of course you have to have well characterized qubits, and you have to have loads of them. The second condition or second criteria means that you need to define nicely what is your starting position when you start your calculation, and how easily this state can be achieved. The third just means that your quantum computer is uh, robust or intact by noise from different kind of sources, that it just is not interfered. Third condition means that you need some set of operations which are necessary to conduct the quantum circuits or quantum computations generally. And the final thing is that you need to, at the end, you need to measure the qubit states. Uh, you need to somehow mine the information out of the architecture. So with these criterias, I will move forward to this quantum-based quantum computers based on molecular spins. These are some of the like nicest molecules I found, or for me it is this, and the construction principle is as follows. The thing is that so-called single ion magnets are used. So and so you can imagine this as the like, smallest nanomagnet you can create. I think yeah. And to create this, you take an element from an F block of periodical table, you put it in the center, or you take an ion, and then around it you put some um, ligand fields, or some other, it might be organic molecules that create something like complex structure with this heavy ion. And um, here in this case you can see that the heavy ion is this terbium in oxidation number 3. Um, the the ligand field here, this large organic molecules, can be quite easily adjusted just by modifying the structures. You can see there are many like hydrogen ending here, and you can combine different ligands uh, in order to alter the electronic structure, yeah, electronic structure of this ion, because on itself it's not so interesting, but when you create hyperfine structure enough, um, you can observe some nice features. Um, um, sorry, yeah. Um, the thing here is uh, s- yeah, thing is that you want to have this F element in with one unpaired electron, in order to have like the system with electronic spin not equal to 0. And this electronic spin creates some interacts with some static magnetic field, and you by applying this static magnetic field, you distinguish different energy levels. Well, whenever the whenever the spin is aligned with the magnetic field or against it, and um, as this magnetic field can be tuned uh, really with nice precision, then you can by adding some come on work yeah, by adding some microwave radiation, you can tune the exact resonance frequency or resonance energy of this energy level splittings with the energy of the radiation, and then you can alter the states here. You can transfer between states 0 and 1. The one of the or there are several sources which no, just say I would like to here I would like to address one of the criteria shown before, and it's the coherence times. It's the stability of the qubits, and the main sources of the noise that can lower these decoherence times is either the thermal vibration of everything that surrounds the qubit, the physical realization of or the molecule, and by uh, uh, by using rigid molecules like was shown in the previous slide, you can somehow protect your element in the middle just by not populating the vibrational modes of those molecules, and therefore you can like solve this source of noise. Then there is interaction with nuclear spins, and mostly it's hydrogen and nitrogen, and these things is not like easily to be solved, because if you want to create these ligands using organic chemistry, therefore there will be probably some hydrogens or carbon 13s which will interact with this. But the really large source of noise generally is electronic spins, or the magnetic fields that from from external sources. And there is nice way how you can counter this interaction, and it's called spin clock transition. It's clock transition because it is somehow used in like atomic clock design. And what you saw on previous slide was this. It's called normal Zenon Zeeman transition, just normal splitting. But if you use ligands well designed, so that there is some energy of magnetic field, that at some intensity of magnetic field, there is some coupling between these two states, you create something like this, which is avoided crossing, can be described as avoided crossing system. And the thing is that here you have quite large energy differences, and when it comes to the closest point, you have the derivative of these energies are with the magnetic fields are zero. Therefore, some the probable transition probabilities between these two states are as well really low, are almost zero in using some approximations. So the only thing is to use to create a ligand field so that this gap is large enough to prevent tunneling between these two states. And by this, you can achieve the decoherence times up to 80 microseconds, which is quite nice. But just to claim this 80 microseconds were measured by really optimized conditions, like that not only use this spin clock transition protection, but also they diluted the molecules with some other which are not active, or which are not which cannot cause these magnetic disturbances. And so this is some like really the ideal conditions, but it is quite nice long decoherence time. And by tuning the system even more, you can create this different spin clock transitions. So you can like get cover or shield the different uh, intensities of the magnetic field from interfering with your spin states. And the thing is that you can by putting some magnetic field here, you can uh, uh, like force the system to be in this exact or here it is nice, better visible, in this exactly avoided crossing point. So there is almost no transitions happening, and there is a chance that there is some like suggestions of possible realization of quantum computers that you can specifically put several qubits in this clock transition position with specifying a magnetic field. And if you want to do some operation with some other qubits, you just unlock them by uh, sorry, by changing the magnetic field and then tuning the or tuning the magnetic field to somewhere else. Sorry for the cough. So this is really nice feature of this more single ion magnets. And to um, play with the structures even more, one can combine different elements within one molecule to create multiple qubits in one molecule or qubits. And here you can see the splitting of cost originating from different from different uh, elements. So this is how you can. I'm sorry. I need to drink something. So you can create these small cells or how to say multiple qubits within one molecule, and of course you can do some quantum computation on within one molecule, which is which is um, quite nice in regard of the noise. So just to show you how different molecules can be coupled together, here there are put on some superconducting matrices in which there is a wire in which I don't understand this precisely, but the microwave photon can be like captured in here, and thus providing some coupling between these two different spin ion magnets or single molecule. Sorry. And this is it's just I think they created only coupling between two molecules, but this is some systematic way how to connect multiple molecules to scale up the system. So to confront this molecular spin magnets with the criterions shown before, you can see that there are some criterions are okay, but the scaling within few qubits within one molecule is very nice. It can be well defined. Therefore, this okay for the second part. But the scaling up the system to combine it with different to combine different sims with this to combine different sims together is that's what is under like, research right now. You it's not really clear how you start your calculations or how you initialize the qubit the well-defined starting point as if you want to cool the system in order to put the all spins to the ground state, you need really like microkelvins or even low temperatures, and it can be done for a few molecules, but it's problematic for larger and fast quantum computers. decoherence times are okay. You can create universal set of gates really nicely. And the measuring is again a little bit questionable. It can be done with this electron paramagnetic resonance, but the thing is that you cannot yeah, you need to combine different approaches, some direct measurements with some indirect measurements, and again, it's not clear whenever it will be uh, solved, definitely or not. So I'm sorry for a cough. It somehow slowed me down. But with this, I would like to move towards the last part of the seminar, and this is the quantum computers based on nuclear magnetic resonance. And again, it's using quite similar phenomena, but this time not we are not dealing with the spin of electrons, but with the spins of atoms. The nuclear magnetic resonance is really used analytical technique for analyzing the chemical compounds. So there is some there's a lot of knowledge within the like just casual measurements, but um, uh, here the figure is very the same. Only the splitting here is caused by non-zero orbital angular momentum of atomic nuclei. Um, and as we are speaking of different ele- dif sorry, as the atoms within the molecules have different surroundings. You can see that this atom, this carbon atom is different from this one. It changes the magnetic field uh, around the nucleus, and therefore there is a different energy or different splitting for different uh, nuclei, even if you are speaking about the same element. So this can be then used to create very efficient but small few qubit systems, because you just create something like this for this two qubit system, because there is you have this contribution or splitting of the spin on carbon, which is different from the splitting on the hydrogen. And you can again, by tuning the magnetic field in order to match with the microwave radiation, you can do some unitary operations. There are few really important nice things about these architectures, and you can like your quantum computer is just single simple molecule like this. This can cause a little bit cancer, but it's simple molecule, really simple molecule. And there are many these NMR machines, so it was just necessary to adapt these NMR machines so to play with a really small few qubit system. It's nice, but the scaling up is really problematic. And here are again the Vincenzo's criteria. So there might be a way to scale it up in the same way as was the single ion magnets, but I haven't found some study which will do this. So yeah, it's really highly problematic. You cannot initialize the system nicely, and the decoherence times are much lower than in previous case. So, but there are nice things about implementing this universal quantum gates. at least on those those few qubits systems, and by measuring the NMR spectrum or some induced NMR spectrum, you can indirectly get the find the measurements of these things. So uh, with this, I am about to conclude the second part of my talk. Just some take-home messages that these quantum computers based on molecular spin uh, uh, are really highly adjustable. You can create these single molecules with hyperfine structure in order to fit your imagination, whatever. And the biggest advantage of this of quantum computers based on nuclear magnetic resonance is that it's really easily uh, uh, creatable. Like you can just buy the molecules from Sigma Aldrich and put it in modified NMR and here we go. But in both cases, the scaling and measurement are questionable, but the scalability is questionable in all cases. I would say, right. So with this, I would like to thank um, and all experimentalists that I worked with, the theoreticians from the Slaviček groups, in which I was in Prague. And I would like to thank my colleagues from quantum dynamics of structure part of quantum computing labs for some nice discussions and so on. So yeah, thank you. If you have any questions, feel free to ask. That's it.
Yeah, thank you for your talk. And surprisingly, we have a question in the chat. So,
Yeah. Do you have any information if anyone has tested these qubits based on molecular spins on in practice? There are some papers in which they I'm not sure which, but they showed simplified algorithms solving some really simplified algorithms. Like they are using it.
yeah, because you said that they are easily creatable, right? So maybe
Yeah, I was the thing was that yeah, here where is sorry.
because it's interesting technology, maybe. So maybe let's wait for some other question.
Yeah, you can. I'm still sharing it, right? You can have a look at
Yeah,
this
okay,
molecule, which can be used as a 4-qubit quantum computer.
great.
Yeah, and this can be bought, right, or
Uh-huh.
synthesized like within few
Yes,
days. Like this is nothing special. So that's the real
I think this
the,
is a really important message, you know? Yeah,
yeah, but the scalability
yeah,
is
great.
questionable, really questionable.
Yeah.
Oh,
Okay, of course. And let's wait for a while, maybe 1 minute for another question. I just want to say that there are no stupid questions. Well, maybe I want to somehow close this seminar, but maybe before we close this seminar, I have to maybe invite everyone to next seminar that will be from this, I mean, from this series, from this quantum computing series, and it will be February 13, so 13th February next year, and the speaker will be Sylvia Ilesova, and the talk of her will be the title is state averaged orbital optimized variational quantum eigensolver where quantum chemistry meets quantum computing. So it's, I suppose, maybe could be another interesting talk, and I think don't miss this another interesting talk. So if there are no other questions, thank you again all for attention, and thank you again, Michal, Belina, for interesting talk, and maybe see you next time, maybe on Friday. So goodbye.